Today I want to show you just a quick short lesson on a concept that's called factoring grouped polynomials. And this is really getting at a little bit of what's to come when we're factoring trinomials in our next example, but it also hinges on what we just learned about factoring out. And so if you haven't watched the factoring out video, you might want to do that. Anyway, you can take expressions like these that have 4 or 5 different terms in it, and you can write these as multiplication problems. And sometimes the multiplication problems are a little simpler to look at than all of these terms. And so that's going to be our goal, is to rewrite these polynomials as multiplications of, well, as compact as we can. So, excuse me. So that'll be our goal. To start, I want to review what our table multiplications look like. So earlier, you may have seen me show you how to multiply polynomials by using a table. And here I've got kind of the results of some multiplications that have been done, but I kind of pulled out the original question. So it's hard to look at this and see what the original question is, but that's my goal. I want to figure out what was the original 2 things that I multiplied to create these tables. And one way to do that is to look at common factors. If I look at say this row, is there anything that this row, both of these terms, have in common? And that's probably what was here. And is there anything that these 2 things have in common, and so forth? So right away, I see that x squared and 5 to the x, they both have an x in common. So that suggests to me that maybe this was an x to start off with. And let's see, if this was an x, what would this have to be to get x squared? Well, this would also have to be an x. X times x would give me x squared. And if this was an x, then this circle would have to have been a 5, because 5 times x would give me 5 x's. And let's see, if that's a 5 and this is 35, well, the only way to do that would be 7 times 5. And notice if this is a 7 and this is an x, 7 times x gives us 7 x's. And so I'm pretty sure we nailed it. I think these were the original factors that when I multiply them together give me this. So x plus 7 times x plus 5. I think when you multiply them all out, this is what you get. X squared plus 7x plus 5x plus 35. We could check that by graphing or plugging in a number. Maybe I'll plug in a 0. So 0 plus 7 is 7. 0 plus 5 is 5. 7 times 5 is 35. If I plug in a 0, 0 plus 0 plus 0 plus 35 is 35. That matches. So pretty sure this is right. This one's a little more challenging, but let's look and see if we can find something that things have in common, and we can come up with the original question that gave us this. So I could look at this top row and see what they have in common, or I could look at this first column and kind of write what they have in common, or I could look at this bottom row and see what they have in common, or this last column and see what they have in common. Pick something, somewhere to start, and then once you've picked something, see if you can derive or kind of divide to figure out what the other circles should have been. I'm going to look at this bottom one. I see that both of these terms are negative, and so that suggests maybe this was a minus. And then both of the numbers are divisible by 8, and so maybe this was an 8. If that was the case, if this was a negative 8, well then this term must have been an x, because when I multiply x and negative 8 together, that gives me negative 8 x's. And let's see, if this was a negative 8, then this had to be a 5. a regular positive 5, because positive 5 times negative 8 gives me negative 40. And let's see, if this was an x, this would have to be a 2x, because 2 times, well, numbers 2 here, and then x times x gives us x squared. If we look here, 2 times 5 gives us 10, and x is there, and so yeah, that all works out perfectly. So this table, I think, was originally 2x minus 8 times x plus 5. And you can do this with bigger tables too. If I look at this top row, for instance, maybe, I see that all of these things are divisible by 3. And I see that all of them have at least an x in it. So if I assume that this was in 3x, which it might not have been, but I'm guessing it was, then this term has to be x squared, because 3x times x squared is 3x cubed. And this term has to be 2x, because 2 times 3 is 6, and x times x is x squared. And this last term has to be 7, and a negative, because 3 times, it's a negative 7. So negative 7 times 3 gives me negative 21x's. And let's see, what would this number have to be to give us this bottom row? What times x squared? Well, I think probably a negative 5. Negative 5 times x squared is negative 5x squared. Negative 5 times 2 is negative 10. And negative 5 times negative 7 is positive 35. So this set of 6 terms must have equaled, or must have kind of come from this original multiplication. What I've just done is I factored these. Now technically I factored them by kind of grouping 2 terms together and seeing what did they have in common. And that's why this method is sometimes called factoring by grouping. So let's do the same thing with these expressions. Here I've got a big long expression, and I want to see if this is the answer to a multiplication problem. And so to do that, you could write it in a table. Let's put those 4 terms in a table. And remember, we've done enough of these table problems that you notice that x squareds go, the highest powered stuff goes in this corner, the number part goes in this corner, and then the middle things go in the middle boxes. So let me just write them in here. X squared, 8x, 3x, 24. And, well, this suggests an x in common and an x here, and that would have to be a 3, because 3 times x is 3x, and this would have to be an 8 to get us 8 x's, and 3 times 8 is 24. That all worked out perfectly. And so that suggests that this polynomial in standard form is equivalent to this polynomial, which is in what we call factored form, because it's a multiplication problem instead of a sum. So, if we look at this example, I think we can use this in a table too and see if we can factor that. If we put the sloppy box. If we put the 3x squared here, the highest powered term in this corner, and the lowest powered term, that is the number, in this column, and we put our 8x's and our 6x's in this diagonal, let's see if we can pull anything out in common. These 2 numbers are both divisible by 2, and that's about all I can see that they have in common. So if this is a 2, then this has to be a 3, because 3 times 2 is 6. More than that, it's got to be a 3x, because 3x times 2 gives me 6x's. And 2 times 8, 8 times 2 gives us 16. And let's see, if this is 3x, this would have to be an x. X times 3x is 3x squared, and x times 8 is 8x's. That works out perfectly. And so this original polynomial here is the same thing as x plus 2 times 3x plus 8. So there's an examples of factoring, factoring by grouping. And factoring by grouping is kind of a nice thing to know how to do. But the next skill that we're going to learn is a little trickier because the problems will not be broken up into 4 obvious things that I can put into a table and quickly find their greatest common factor. Usually, remember, we combine these things. And so a lot of times it will come at you looking like this: x squared plus 11x plus 24. And that, if we tried to make a table and put it into a table, is a little tougher. I know that the x squareds go here, and I know the 24 goes here, but the 11x actually didn't come. The 11x was the sum of these 2 terms. And so I can't really put the 11x in this box or in this box, but I somehow have to split up those 11x's and put some of those x's here and some of those x's here to reconstruct what came up, and that's not always obvious. So that's what our next video will be about. So be sure to tune in next time to see how do we do that, and use the same technique to factor expressions when they have been combined already.